So look at the whiteboard or scratch paper of a computer scientist or mathematician, and you'll likely see a variety of diagrams, by which I mean schematic representations of structured objects. But as soon as you look at their screens, diagrams become much rarer, and the diagrammatic representations that are most natural to work with are often absent, or take a lot of effort to produce as custom visualizations on top of existing programming and theorem-proving environments. So in this talk, I'm going to first address the question of why does this gap exist? And I think it's because existing systems can't meet the practical needs of these interactive exploratory environments. But an approach that I am seeking to develop in my research, which is compositional diagramming, can, and I'll show you how. And just as a teaser, compositional diagramming is when a diagram is formed as the composition of sub-diagrams mirroring the compositional structure of the object being represented. Here it's a tree. And I hope to develop a better understanding of how compositional diagramming works through the lens of programming languages and formal methods to build a useful diagramming system. So what is diagramming? As I mentioned, a diagram is a schematic representation of a structured object, and schematic means it uses basic shapes and visual principles like grouping or color. And diagramming is the act of producing such a visualization from such an object. Diagramming is not statistical graphing or plotting. However, there are some similarities. When you write, say, a matplotlib script to produce a graph, you might think you're writing a script to produce that one graph, but what you're actually writing is a function that converts data in some expected format into a graph of that format, and as you change the data, the graph will change. In the same way, diagramming is when you specify a function for converting objects in your domain to visual representations. This distinguishes diagramming from drawing, where there is no underlying object, or there is, but only in your head. Still, drawing languages can range from simple to sophisticated, but they're still intended to produce a single drawing or serve as a target language for other tools. Here I have examples from PostScript, which is a pretty low-level language where you specify coordinates and instructions, or you can have higher-level languages like Bluefish for composing drawings from more basic parts. So I talked about diagramming. What is this practical part? What makes a diagramming system practical? And broadly, we claim that an ideal system would make it low cost to specify a diagrammatic representation that the user can immediately start using. And specifically, there are three main features that enable that: canonicity, continuity, and specification idioms. And this comes from some work at HATRA, which was a workshop at Splash 2 years ago, where we asked, we were inspired by how textual notation systems and proof assistance work, and what can we learn from their success. So by canonicity, we mean that equivalent objects have equal representations. Now, to illustrate this property and how a system might fail to ensure it, I'm going to use an example from GraphViz. And this is not to dunk on GraphViz. I mean, it's a great tool. It's meant for visualizing arbitrary graphs and has a lot of controls and knobs for different kinds of graphs. And it's also meant for doing this at scale. So it's unfair to nitpick these single small instances of graphs that GraphViz produces. However, it's a widely used tool, and I'm going to use it as a critique of constraint-based or these global non-compositional approaches to drawing diagrams in general. All right, so in this process diagram, there's two processes. There's a process that goes from A0 to A3 and forms a loop, and then there's a straight line one from B0 to B3, and then there are some crossing edges between the two. And this is part of what the spec for this graph was in the source. And then I thought, okay, well, this seems a bit redundant. Like, I could simplify it by just moving that A3 to before that A0 and should produce the same graph, right? But in reality, what GraphViz produces is a different graph entirely. It rearranges the process A0 to A3 to rotate it by one, and then the alignment is off. And actually, if you look at it carefully, the alignment was always off with the B's. And this is because we never told GraphViz the structural information that we care about, such that, you know, A's and B's are processes that we want to be vertically aligned and keep that order fixed while we change other parts of the diagram. And in many cases, it's actually cumbersome to encode this information in a way that a tool like GraphViz can understand. An ideal diagramming system would make it easy to specify which differences matter for the visualization and which don't, hence equivalence in quotes. The next property I'm going to talk about is continuity, by which I mean incremental evolution is easy to follow. So again, the same graph and another part of the spec where you have these extra edges that go between the A's and B's. And I decided, okay, I'll add a fourth one from B2 to A2. And I would expect that the arrow just shows up between B2 and A2. But in reality, the graph that graph produces with this simple transformation is, again, completely misaligned. Again, and this is not, I'm not critiquing graph specifically, I'm just saying that when you have a non-compositional approach to diagramming, these sorts of problems are inevitable. An ideal diagramming system would have good defaults for continuity, such as using incremental graph layout, but also make it easier to specify how incremental changes are supposed to be visualized, which is especially important for stepwise exploration of proofs and programs. I've said a couple of times that the system should make it easy to specify something. Another way to say this is that the specification language should have idioms for common practical concerns. One common one is, how do you fit in limited screen space? You can wrap, which is trading one axis for another. You can fold, which is to sacrifice completeness to save space. You can pack your diagram tighter together, which might sacrifice clarity. And there might be other ways, other trade-offs. Another common trade-off is composition. So even in this simple diagram with labeled nodes in a tree, I'm composing the problem of wrapping text inside the label with perhaps wrapping the tree itself on the outside. I might want to specify visual styling, which is important for my domain in order to make these graphs look good, and many other properties. To paraphrase Alan Kay, simple things should be easy to specify, and complex things should still be possible to specify. But with existing systems, you can either use a domain-specific tool that makes it simple to do a narrow range of things really well, or you implement your whole custom wrapping and styling with a lot of effort, and there's no middle ground. All right, so I've told you about why I think this gap exists, and I think it's because existing systems can't meet the practical needs of programming in theorem-proving environments. Compositional diagramming can, I claim. Compositional diagramming is when a diagram is formed as the composition of subdiagrams mirroring the compositional structure of the object being represented. Take an example. Here's a tree, and to produce a tree diagram from this object, we would start with the leaf A, which is a circle with the label A, the leaf B, which is a circle with the label B, and I put them side by side, and now I see that they're both contained in a node. So for the node, I draw the parent node, and then I connect it to its children. And I repeat this process recursively, following the recursive structure of the tree, and I get the whole tree diagram. Now, I can't manipulate pixels directly, right? There's something more going on. Let's take a closer look. When I say that the leaf A, when I say that our system turned the leaf into the circle, really it turned it into this term in some sort of slightly lower level language where I have a circle with a label and some ports, and ports is the interface for connections with other diagrams, in this case the location of the center. And that's all that the outside of this diagram needs to know. Similarly for B, it's another circle, and then when I see the node, the parent node, the system first horizontally concatenates the two together, and the ports of this concatenation are the concatenation of the two individual ports, and then there are some spacing and alignment properties. Then I vertically concatenate that with the parent node on top, and whose ports are now just the one at the top, and finally it connects the parent ports to each of the children. In other words, what I just described is compiling objects in this format, the tree, to a higher level drawing language, which may be further compiled to a lower level drawing language like SVG, which is finally executed to produce the equivalent of a binary, might be a rendering on your screen. And this compilation step, using a compositional diagramming system, is exactly specifying that compilation step. I claim that composition lets users control canonicity because users are specifying a diagramming function. They can control what objects are treated as equivalent under what assumptions about the output parameters, like available space. So for instance, suppose instead of trees, I switched to a tree map representation where hierarchy is represented as containment. But if only containment matters, then the order is not relevant. The two squares could be swapped, or if there are more than two, they could be in any order as long as the inner space is filled for this representation. Now, if I give this diagram more vertical space, I can give it the freedom to change how its inside components are laid out if it doesn't matter to me, just to make better use of available space. I'm choosing to trade off, I'm choosing to allow it the flexibility because I view those two structures as equivalent. And so this representation might be better able to adapt to weird sizes. Composition also makes continuity natural. So suppose I started with this tree and I replaced the leaf C by another subtree, which is a node with 2 leaves, C and D. I would just have to replace, because it's compositional, the diagramming function can decide whether and how a change in a subcomponent should affect unrelated parts to minimize unrelated changes. In this case, the unrelated parts weren't affected at all, only the C and D part was changed. In fact, if I undo that step, maybe node C should stay where it was, instead of coming back in tighter. Lastly, compositional diagramming also naturally supports many of the idioms I mentioned before. So for instance, instead of composing bounding boxes, I could compose compositions of rectangles with finer granularity to keep better track of where my objects are and be able to pack them tighter together to match, to fit a target width. Other idioms like wrapping also fit neatly into a compositional approach. And note that here, actually, only the top level tree has wrapped and the inside trees are still using the full tree representation. Okay, so I told you a little bit about compositional diagramming, but is this approach powerful enough to draw the sorts of things we want to draw? So far I showed you trees and tree maps, and from my original slide, well, those two are trees. That's kind of a degenerate tree with some extra annotations. Those two were tree maps, and the rest seem a bit further out of reach. Turns out that there's another class of graphs called series parallel graphs that comes up in various domains like electrical circuits or syntax diagrams. And it's kind of a generalization of trees, where trees are graphs of tree with 1 and SP graphs are tree with 2. Now, since you can't draw these as trees or tree maps, we decided to try building a new layout algorithm, still following the compositional approach to see what we could do with it. So this is a deep dive into a class of diagrams called railroad diagrams that are schematic visualizations commonly used for formal grammars and command languages. So these examples come from a variety of domains. Those two are from the world of Pascal back in the day. And there's a bunch of more modern ones from software manuals and specifications. But despite being so widespread and intuitive, all the ones above were laid out by hand. Now, what do I mean by laid out? There are a number of interesting decisions when you draw a railroad diagram. One of the most interesting ones is that there are two-dimensional drawings, sure, but they still have a linear reading order, left to right, top to bottom. So for instance, this diagram represents a sequence of an open brace and then either just a white space and then a closing brace, or a loop of white space string, white space colon value, separated by commas as many times as you want, followed by the closing brace. So I read that left to right, top to bottom, as I said. And moreover, inner components can independently wrap following that linear reading order, like the circled bit above. So this makes laying out a railroad diagram what I call a 1.5 dimensional layout problem. It's somewhere between just straight one-dimensional layout and full use of two-dimensional space. Other interesting layout decisions include, I'm going to use this example from SQLite. The schema name component and the module argument component are kind of syntactically in the same position, right? There's optionally you do nothing or you do the inside of that option. But why is the schema name on top but the module argument part on the bottom? Or how come one of them seems to enter from the top and exit on the side, whereas the other one enters and exits from the side? Or why are the line breaks where they are? How do we choose to put them there? In general, there are many ways to lay out the same diagram, same being semantically equivalent. And existing approaches to drawing railroad diagrams fall into 3 categories. First, you have layout DSLs, where each decision is manually specified by the user. For instance, creating a stack with 3 elements for the 3 wrapped lines, or specifying how those optional components are to be drawn by using different keywords to say, I want it on top or on the bottom. Still, the DSL often constrains the space of possible outputs to not have all the niceties we saw earlier, like that merged edge coming in from the top. A second approach is grammar translation tools, where a grammar, here a JavaScript regular expression, is turned into a railroad diagram with some automatic decisions from the tool. But these tools often have an even more restricted range of outputs, producing diagrams that are more complicated than they need to be, like in that box, or performing no wrapping at all, or giving the users no control over alignment and visual style. All those decisions are already just made and fixed by the tool. The third category is, of course, specifying the diagram in a low-level drawing language, and it's not diagramming at all. It's completely separated from the object that it used to be. But as I was saying before, in this trade-off space of tools, the middle ground doesn't exist. An automatic diagramming tool that meets practical needs while still being able to reproduce a reasonable range of what people can draw by hand. Our approach was, of course, to treat it as a compilation problem. So we have a source language, which is this language of diagrams, and it has tokens and sequences and disjunctions and loops. And our target language is a language of layouts that have more layout-specific details like widths and directions. Now, these extra details have to line up to make a sensible diagram. For instance, here the L2 has to be in the opposite direction as L1 because it's in the loop part. In other words, layouts have to be well-formed. Luckily, we managed to make the well-formedness rules fit on one slide. Now we can define what laying out a railroad diagram means. It means just the same as any other compiler correctness. You're converting a diagram to a layout such that the decompilation of the layout back to a diagram are equivalent and the layout is well-formed. Next, we implemented a compiler that follows the specification and is well-suited for practical use. So there are 3 steps in our compiler, which is vertically aligning the components of the diagram, wrapping components across rows, and horizontally justifying the distribution of space. Each step corresponds to some of the well-formedness and correctness properties I mentioned above. Further, wrapping is the only step that has to be phrased as an optimization problem, and we found that composing local wrapping decisions for each component was enough to reproduce practical layouts. We didn't have to do any global non-computational reasoning. The alignment and justification settings I showed earlier are also just direct specifications, also local and compositional. As an example of how our compositional approach enables canonicity, here's a layout produced by our compiler. There's a 3-way choice on the bottom between the primary key unique stuff, check, and foreign key, etc. Disjunctions are binary. Disjunctions are the blue pluses. So there are actually 3 ways to express that. There are 2 ways to express the 3-way disjunction. I've associated them one way on the slide right now, but if I reassociate that term, it doesn't matter. We want them to produce the same diagram. As for continuity, suppose I wanted to replace the expression part with making it optional. So I add a disjunction with one branch that's optional and the other branch that's what it used to be before. Watch what happens to the diagram. There's plenty more I could say about this work. I'll be happy to chat afterwards. You can check out our preprint about it. The code is available on GitHub, and there's also an online playground you can actually play with this tool in. All right, so I talked about compositional diagramming, including some previous work and ongoing work. Now I want to talk about the future, mostly. I want to conclude by outlining a few directions of research that I think will help me build a useful diagramming system, and I'd be happy to hear your ideas about them at the end or chat afterwards. The first is working towards a diagramming specification language. I think that most diagrams that we use in programming and theorem-proving contexts can be seen as and drawn as a core compositional structure with some extra edges on top. Trees and tree maps weren't quite enough because then I had to work on these railroad diagrams separately. But if we also have a series parallel graph layout, is that enough? Or do we need more primitives? This is something I'm still thinking about. Beyond these cores, I've talked about specification idioms that would make diagramming more practical, such as compositional packing, or viewing wrapping and folding as these local, composed, combinatorial optimization problems. But so far, I've only looked at self-similar diagrams, where each diagram is recursively composed of parts that are just like itself. And I kind of have a sense of what primitives or what interfaces you need to be able to get this problem to work out. What about when I'm composing different diagramming domains? So what sort of primitives do I need for those? And going further out on a limb, I spoke about continuity and how being able to visualize transitions between steps as you explore a program or proof is important. How do we animate those transitions? How do we use the structural information that we have about rewriting rules or steps in a program to actually display those in a continuous way? And there might be other practical considerations I haven't thought about yet. A different line of research I'm interested in exploring is railroad diagrams can represent the control flow of some programs. So for instance, this might be a diagram to represent just a conditional. This one might represent a loop, but it could also represent this recursive program where I say, if the condition is true, then you go straight out and you do T, otherwise you do E, and then you recurse. And the recursive call here is in the tail position, which is why I can draw it as a loop. Which programs exactly can I represent the control flow using railroad diagrams? On a different note, pre-printing code is a problem where formal approaches have been particularly fruitful in programming languages. Can pre-printing be encoded as a railroad diagram layout problem, or what can I learn from existing fruitful approaches to pre-printing and adapt them to how I do railroad wrapping? So to recap, I think diagrams are rare in our programming and theorem-proving environments because existing techniques can't meet practical needs. But an approach that I am trying to develop, which is compositional diagramming, I claim can meet those needs. And I aim to use programming languages, formal methods, inspired perspective, and techniques to build a useful diagramming system for the working computer scientist, programmer, and mathematician. Thank you.